Pick out the true statement. Every group of order 36 is abelian. So a group can be classified based on order. Based on order, group may be either finite or infinite. Basically, I am understanding that you know the meaning of order, or in other words, you can say size of the group. Finite means fixed size, means number of elements are fixed, and infinite means there is no counting of the elements. But one correspondence may be possible as we see counting in real analysis. Sometimes we say cardinality of the set. So option A is saying every group of order 36 is abelian. For this we consider D18. Order of this group is 36, but this is not abelian. Non-abelian, non-abelian, because Dn in general Dn is non-abelian, implies that non-cyclic, because we know that cyclic groups always, or cyclicity implies commutativity. By negation of the statement, a non-commutative group implies that non-cyclic. So option A is wrong, means false statement. But it doesn't mean group of order 36 may not be cyclic. You can consider Z36. This group is cyclic as well as abelian, because of cyclicity implies commutativity. So group of order 36 may be abelian or may not be abelian. If order of the group, let's say order of the group, you can write as p square, where p is prime number, then group is necessarily a abelian group. 36 you cannot write as p square type, because 6 is not a prime number. That's why this group is not necessarily abelian. I have the examples already explained using examples. Now come to the option C. Every group of order 36 is non-abelian because of every group. So order 36 group may be abelian. You can consider Z36. So this statement is again wrong statement. A group in which every element is of order at most 2. We know identity element is always of order 1. Whatever the group, cyclic, non-cyclic, abelian, non-abelian, finite or infinite, identity element always there in the group. So order we can find of identity element, and order of identity element is 1. But statement B is saying every element is of order 2. It means order may be either 1 or 2. Order 1 element is identity, and order 2 you can understand that there is non-identity element. There is non-identity. If there is non-identity element, then order of that non-identity element is 2. For this, keep remember K for Klein for group. Order of non-identity element in K4 is 2. So statement B seems true. I am not saying exactly, but seems true. If you consider trivial group, then statement again seems true. So in general, we will try to prove statement B. Let's say A and B both are element of a group. Let's say AB, A comma B, both are elements of a group, then by closure, product of these is again group. Now consider that non-identity element is of order 2. I am saying because identity element is of order 1, that's why non-identity element is order 2. If A and B are non-identity element, then their product may or may not be identity. If product is identity, then order 1. If product is non-identity, then is it of order 2. So if order is 2, then AB square equals to identity. I can write AB equals to identity. This is the meaning of writing in power or expanded form. Now, because AB is element, so you can post multiply by A inverse. So after post multiplying by AB inverse, what we have in left hand side and right hand side, you can see on my screen. Now, by Sox's property, inverse come in reverse order. So B inverse, A inverse, and in left hand side AB. So AB equals to, because I already told you A and B are non-identity elements. So these two are of order 2. Order 2 means self-inverse element. So B inverse is B and A inverse is A. Now this is condition AB equals to BA for all AB coming from G. So statement B is true now.